Welcome back. In this lesson, we're diving into the fundamentals of networking. It's an essential skill set for AV professionals today. Understanding networks means you'll be ready to design, install, or manage AV systems that connect seamlessly with IT infrastructure. So, what is a network? A network is simply a collection of interconnected devices that can communicate and share data. You probably encounter networks daily. Think about your smartphone connected to Wi-Fi, for example, or the computers at your workplace sharing files and resources. To get us started, let's talk about how networks are categorized. Typically, networks are identified by the geographic area they cover and their functional purposes. We're going to go through the most common types now. First up, the local area network. A LAN, or a local area network, connects devices over a relatively small geographical area, like an office, building, or home. LANs allow devices to easily share resources such as files, printers, or AV equipment. Usually, a local area network is privately owned and controlled by the end user or organization. When you remove the cables from a LAN, you have a wireless LAN. Wireless LANs use radio waves to connect to devices like laptops, smartphones, and tablets to the network. They offer more flexibility for mobility and collaboration. Next is a campus area network. A campus area network interconnects several local networks within a larger defined area, like a university campus, a hospital complex, or corporate campus. Campus area networks are often called CANs. They allow multiple buildings to share resources and centralize IT management. As we go larger, we find the metropolitan area network. This expands further. A MET area network covers an entire city or a metropolitan region. Commonly, these networks are used by governments or large companies to provide high-speed connectivity over a city-wide area. At number 5, we have wide area networks, or WANs. These span broad geographical areas. Think countries, continents, even the globe. The best example is the Internet, connecting billions of devices across the world. WANs typically involve specialized routers and leased telecommunication lines. Next, we have the storage area network. A storage area network is a dedicated, high-speed network specifically designed for data storage and retrieval. Companies often use those to manage a large database, media archives, or backups. A common network that you will encounter in your day-to-day job is a virtual local area network, or a VLAN. This is slightly different. A VLAN groups devices logically into one broadcast domain. Even though such devices might be in separate buildings, VLANs group them as if they were in the same local area network. Stretching VLANs across locations is not recommended in my opinion. VLANs increase security and manage traffic flow efficiently within larger networks. And finally, we got a personal area network. This is the smallest type. It only covers a few meters, connects personal devices like smartphones or Bluetooth headphones, smartwatch, or fitness tracker. To recap, LANs and wireless LANs serve smaller areas like homes and offices. CANs and MANs connect larger areas such as campuses and cities. WANs connect devices across extensive distances, think countries or globally. SANs manage high-performance data storage networks. VLANs group network devices logically, and PANs provide personal short-range connection for everyday devices. By understanding these different types of networks, you'll be better prepared as a professional to communicate effectively with IT teams and troubleshoot network issues on site. But more importantly, you will be able to successfully integrate AV technologies into any networked environment. Now that you understand the basic network types, let's move on to how networks are physically and logically connected. This concept is called network topology. Understanding a topology helps you make the right decisions about setting up, troubleshooting, and scaling your networks. In its essence, a topology refers to the way devices are physically or logically arranged to communicate within a network. You will hear often network engineers calling those devices nodes. Think of a topology as the blueprint or a layout plan for your network. The physical topology is how devices and cables are physically connected. The logical one, on the other hand, is how data flows between devices regardless of their physical arrangement. A star topology is one of the most common network setup. In star topology, all devices are connected directly to one central point, usually a switch or a router. The central node manages all network traffic. It is easy to manage and troubleshoot, and failure of one device does not affect others. However, if the central device fails, the entire network goes down. Next up, we have the bus topology. A bus topology connects all devices along a single central cable. Every node listens for data on this single shared channel. A bus topology connects all devices along a single communication line. Every node listens for data on this single shared channel. It's easy and inexpensive to set up. It's for simple, very small networks. Remember that if that shared channel fails, the entire network goes offline. It's very difficult to troubleshoot and scale. Although they are uncommon today, they are used in specialized scenarios. You will see them maybe in lighting control systems and building management systems. Next, we have a ring topology. Each device connects exactly to two other devices, forming a closed loop or ring. Data travels in one direction, passing through each node sequentially. As a topology, it's easier to manage traffic and bandwidth. A break in the ring, however, can interrupt the network unless redundancy is considered. You will find ring topologies in telecommunication systems sometimes with backup paths. Next, we have the mesh topology. A mesh connects each node to one or other nodes. This creates multiple data paths, ensuring high resilience. If one node or connection fails, data reroutes automatically. It's highly resilient, excellent for critical applications, and the multiple pathways enhance reliability and redundancy. It's expensive, of course, due to extensive cabling and equipment, and it can be complex to set up and manage. They are popular in wireless applications, building automation, and especially in the IoT, where continuous connectivity is crucial. Hybrid topologies blend two or more different topologies into one network. For example, a combination of star and ring or star and bus. They are flexible and scalable. They combine the strength of multiple topologies. They can be tricky to set up and manage, however. They are common in larger organizations, campuses, and modern installations. They have been designed to meet diverse needs. Tree topologies or hierarchical topologies expands a star network into multiple layers. Think of it as several star networks connected by one central star. It's highly scalable and organized. It's easy to expand by adding new branches, and if the central hub fails, entire branches lose connectivity. Tree topologies are widely used in corporate networks where multiple departments or floors need structured yet centralized management. A few more topologies that I would like to mention. The first one is the three-tier architecture. This is the standard architecture you will find in a large enterprise network. It comprises three crucial layers: the core layer, the aggregation, and the access layer. These layers undertake different connections and functionalities, and they aim to enhance the network's architecture performance and reliability as well as flexibility. Since it is a predominant network structure in use today, it has a number of advantages. It has an enhanced performance and ease of maintenance, very flexible, very scalable, and highly reliable. A variation of such architecture is the collapsed core. Unlike the three-tiered architecture, it is a two-tier network, collapsing the core and the distribution layer. Finally, a very popular one in media networks. It's called the spine and leaf architecture. It is a derivative of a data center network topology that uses two layers of switches. The cores are the spines and the leaves are the axis ones. It offers improved scalability, low latency, and high availability by connecting all leaf switches to all spine switches in a full mesh configuration. You might ask yourself, why is this important? As a professional, understanding network topologies enables you to design reliable and efficient and maintainable networked AV solutions. Each topology choice impacts cost, performance, and resilience of the overall system. So let's recap. Star topologies are centralized, simple, common. Bus is inexpensive, simple, and maybe suitable for micro setups. Ring topology, I see these in live environments. It has predictable data flow, commonly used in telecommunications sometimes. Mesh topologies are highly resilient, excellent for critical connections and IoT. Hybrid combines benefits of multiple topologies, adaptable to complex needs. Tree topologies are organized hierarchy, scalable for larger networks. We also talked about the three-tier architecture, two-tier collapsed core architecture, and we also covered the spine and leaf architecture. Now you have a clearer understanding of how networks are physically and logically structured. With this, you can be better equipped to design and support reliable solutions in any network infrastructure. So now that we explored network types, let's dive deeper into Ethernet. Ethernet is an IEEE standard to ensure consistent and reliable data communication between devices, formerly called the IEEE 802. It defines how devices exchange information, outlining the physical connections like cables, fiber optics, or wireless, as well as the logical structures that manage data flow. Ethernet uses a packet-switched based system. This means large files or data streams are divided into small pieces called packets or frames. Packets can take multiple paths across a network, which sometimes means they arrive at their destination out of order or even get lost. The receiving device keeps track of incoming packets, reorganizes them, and requests missing information if required. The default Ethernet approach is known as a best effort system. It means the network tries its best to deliver data without guarantees, making it extremely efficient and flexible. Although, if you have control over such network, you are able to define priorities and get around the best effort system. To physically connect devices using Ethernet, twisted pair copper cables are the most common. These cables are terminated with a connector known as an 8P-HC modular connector, or the more common name, an RJ45. Within the Ethernet standards, there are two primary wiring schemas, T568A and T568B. The 568B is the common standard in commercial AV. Interestingly, if you connect one end with an A standard and the other with a B standard, you create what is called a crossover cable. This cable allows two computers to directly communicate without needing a switch or a router. This helps sometimes in troubleshooting small setup. Note that most modern network devices, including routers, switches, and computers, have auto MDIX, which automatically detects and adjusts for cable type. So the need for special crossover cables is something that we don't have to think about anymore. So what happens when we need higher speeds? Ethernet often uses fiber optic cables. These cables transmit data as pulses of light through strands of glass or plastic fibers, each as thin as human hair. Fiber optics easily handle speeds like 40 gigabits per second and can even scale up to hundreds of terabits per second. This actually makes fiber optic the future-proof choice for networks that anticipate growth. There are two main types of fiber: single mode and multi-mode. The single one, it carries signals over longer distances using a single light path. The multi-mode carries signals over shorter distances through multiple light paths. There are multiple connectors for fiber cables, each serving different purposes. The most common connectors are ST, LC, and SC. SC uses a simple click-to-lock mechanism. The LC is known as push-pull connectors. They are very easy to plug and unplug, and you got the insert and twist style. The ST ones, they are very similar to BNC connectors. Of course, Ethernet is not limited to physical cables. Wireless Ethernet, known as Wi-Fi, is defined by the IEEE 802.11 standard. Wireless is continually evolving, with current standards allowing theoretical speeds up to several gigabits per second, and future developments promising even higher speeds. The actual connection speed, however, depends on factors like signal strength, distance from the access point, physical obstructions, and network congestion, of course. Wi-Fi connectivity commonly relies on an access point, which acts like a hub that converts wireless signals into wired Ethernet frames and vice versa. The most common factors affecting performance are distance, so shorter distance provides stronger and faster connections, obstructions like walls, metal objects, human bodies as well, and of course the load. So more connected devices means shared bandwidth, potentially slowing down the network. The IEEE updates the Ethernet and Wi-Fi standards on a regular basis to keep pace with technology. These standards ensure consistent and interoperability between devices manufactured by different vendors. Remember that the Ethernet standard is labeled as 802.3 and the Wi-Fi standard falls under 802.11. So to recap, we learned about Ethernet. It's governed by the IEEE 802. It's the primary method for data transfer in local area networks. We understood that data travels in packets, which can take any route through a network. We understood that wired Ethernet uses twisted pair copper cables and RJ45 connectors. And also fiber optic is an option that enables high-speed, long-distance Ethernet connections. And we also learned that Wi-Fi provides flexible wireless Ethernet connection with speed depending on proximity and signal conditions. Understanding this and understanding how Ethernet connects devices is essential for AV professionals. With these fundamentals, you'll confidently interface AV equipment into any IT infrastructure. Since you're integrating audiovisual systems into IT infrastructure, understanding the foundational models of networking is crucial. The two primary models that will frame your understanding of network communications are the OSI model and the TCP/IP model. Each provide a conceptual, structured approach to networking, clearly delineating specific functions across various layers. We'll start by the OSI model. It's a conceptual framework, has 7 layers. It's developed by the ISO. It is a theoretical framework that standardizes the functions of a telecommunications system into 7 distinct layers. From the bottom up, the physical layer deals with physical connections between devices. It identifies cables, switches, and the transmission of raw binary data. As we go up, we find the data link layer. This ensures error-free data transfer between adjacent network nodes and manages protocols for establishing and terminating connections. The network layer handles data routing, forwarding, and addressing. The optimal path for data transmission is determined here at this point. We go up to the transport layer. This provides data transfer between end systems, including error detection and correction, as well as flow control. The session layer manages sessions between applications, establishing and maintaining and terminating connections. The presentation layer translates data formats between applications and the network. This ensures the data is readable by the receiver. And finally, the application. This facilitates end-user applications and interfaces. Think of your web browser, for example. This layered approach allows for modular troubleshooting and development. Since each layer operates independently, yet it interconnects with the adjacent layer. This segmentation is particularly beneficial in complex AV systems where pinpointing an issue quickly is essential. For me, I personally prefer the next model, the practical standard, if you like. The TCP/IP model, in contrast, is developed by the US DoD. It is a more streamlined framework that underpins the modern internet. It consists of 4 layers only. From the bottom, we have the network interface layer. This corresponds to the OSI's layer 1 and 2, physical and data link. It manages physical transmission of data. Next up, we have the internet layer. It aligns with the OSI's network layer, handling addressing and routing through protocols like IP. And in the third level, we got the transport layer. It's very similar to the OSI's transport layer. This layer is about data transmission using protocols like TCP and UDP. And the application layer, which combines functionalities of the OSI session, presentation, and application layers, supporting end-user applications. The TCP/IP model's consolidation of functions into fewer layers reflects its pragmatic design and emphasizes efficiency and real-world applicability. The protocols are the foundation of internet communications. Makes it an indispensable knowledge for professionals working with networked systems. Both models serve to standardize network communications. Remember that they differ slightly in structure and application. The OSI offers some sort of granular view, whereas the TCP/IP layers consolidate functions. This is a more streamlined approach, if you like. So let's cover network interface cards, MAC addresses, and IP addressing. We'll also cover subnet masks and the difference between static and dynamic IP addresses. Understanding these basics is critical for a successful AV and IT network deployment. Every device connected to a network needs a network interface card, NIC for short. Think of a NIC as your device's door to the network. Historically, NICs were separate hardware cards inserted into computers. Today, they are usually integrated directly onto the main board or embedded within devices. Wired NICs typically use Ethernet connections with RJ45 connectors. Wireless ones translate radio frequency signals to digital data. Each NIC has what you can call a unique identifier. This is commonly called Media Access Control Address or MAC address. Think of a MAC address like your device's fingerprint. It's unique. No two are the same. MAC addresses are 6 bytes or 48 bits. They are represented in hexadecimal often. They have 2 parts. The first half identifies the manufacturer. The second one is a unique serial number. It's used by network hardware, switches, routers, for example, and end hosts. Network devices like switches and routers use these to identify and route data at layer 2. It's essential for connectivity, network security, and troubleshooting. Now that your device has a way of physically connecting to the network using a network interface card and a unique hardware identifier, which is the MAC address, so how does it join the network and communicate with others? This is where network addresses or IP addresses come in. Think of it as an identifier and a location on the network. Recall that we talked about the OSI and the TCP/IP stack. IP addressing operates at layer 3, the network layer. The traditional format is called IP version 4 or IPv4. It's developed in 1982 and it's still the most common today. IPv4 is often written in dotted decimal. It's 32 bits in length. And it's written in 4 groups separated by dots, and those groups are called octets. Each octet ranges from 0 to 255. You can break down those dotted decimal numbers in binary if you want. Since it's 32 bits, it supports about 4.3 billion addresses. We almost exhausted all of them, or we have exhausted all of them. To overcome this exhaustion and limitation, IP version 6 or IPv6 was introduced. It offers an almost limitless supply of addresses. IPv6s are 128 bits long, displayed in 8 groups of 4 hexadecimal digits. It supports approximately 3.4 times 10 to the power of 38 addresses, virtually unlimited. It improves routing and efficiency and network security. If you decide to get deeper into networks, IPv6 operates in a different manner than IPv4, and some protocols are improved when they operate in IPv6. IPv6 can also integrate a device's MAC into its IP addressing, making addressing easier and more automatic in certain environments. Now that we identified a device at the network layer using its IP, we need to know its location. Subnet masks help us with this. They help networks organize devices into smaller logical groups called subnets. And as a byproduct, it improves network efficiency and security. A net mask separates an IP address into 2 parts. The network portion, it identifies the network where the device is hosted, where the device lives, and the host portion, which identifies the specific device within that network. So a mask of 255.255.255.0 indicates 254 possible hosts in one subnet. So let's talk about how hosts pick up those addresses. From a high-level perspective, there are 2 ways: static or dynamic. A static address means that it's manually assigned and never changes unless explicitly updated by an administrator. It's often used for devices that must be consistently accessible. Think of servers, video conferencing systems, and control systems. To assign a static address, you will need an IP address, a subnet mask, and the default gateway, as well as a DNS server. Remember that static addressing should be used with caution because the burden of administrators is heavy and it's not highly scalable, so only use that when needed. Dynamic IP addressing automatically assigns IP addresses through a service called Dynamic Host Configuration Protocol. It simplifies network management and automatically avoids duplicate IP addresses. Also less burden on administrators. The disadvantages of this: IP addresses may change if the lease expires, which makes certain connections or remote control difficult without DNS. You can reserve addresses through DHCP though, so I wouldn't count that as a huge issue. This is where the hybrid approach comes in. The hybrid approach, or reservations if you like, it involves reserving certain IPs in the DHCP server for specific devices. It combines the advantages of DHCP and static addressing. It requires the person who controls the DHCP server to reserve IP addresses based on MAC addresses. For example, you can have your AV control panel always receive the same IP, even though the rest of the devices are dynamically assigned. Remember that AV systems are becoming more and more network-based, so understanding these concepts is essential to properly design, install, and troubleshoot AV solutions. And correct IP addressing ensures reliable system operation, and knowledge of MACs helps you secure and optimize your network resources. And remember that effectively subnetting provides improved performance, security through segmentation, and scalability. So, to quickly recap, a device needs a network interface card to communicate on networks. MAC addresses are unique hardware identifiers. IPv4 and 6, they are two methods to uniquely identify and communicate on layer 3 networks. Subnet masks are logical subdivisions of networks. Static IP is fixed addresses for critical devices. DHCP automatically assigns addresses to devices, and the hybrid approach is using DHCP reservations. Now that you have the foundational knowledge and you understand how devices are uniquely identified and connected on a network, you are ready for success in your AV and IT integration journey. So now let's explore DNS and how devices locate each other through domain names rather than memorizing numbers. DNS, or the domain name system, is the Internet's phone book. It translates names to IP addresses. So why DNS matters? A, it's highly scalable, and of course it's easier for us to remember and use domain names rather than numerical IP addresses. That means that we can connect to websites and network resources more efficiently. Every time a device connects to a network, the DNS server links that device's name to its IP address. And this way, instead of remembering complicated numbers, you simply type google.com or youtube.com. DNS with DHCP, when used together, they simplify network management. DHCP enables automatic IP assignment, and DNS allocates the host name for said IP. Now let's dive into some foundational network devices. At the edge of a network, you'll find switches. Switches connect multiple devices within a local area network. It enables them to communicate efficiently. Switches commonly operate at layer 2. They save each device's MAC address in a memory called the CAM. Frames are switched directly to the intended recipient or destination device based on MAC addresses. Switches can handle devices with different speeds simultaneously and optimize data flow. There are two main types of switches: unmanaged and managed. Unmanaged ones are dumb switches. They are plug-and-play devices, no configuration needed. They are simple for testing, not production environments. Managed ones allow advanced configurations for speeds, VLANs, QoS, and so on. They are used in complex networks to monitor and manage traffic efficiently. In layer 3, you will commonly find routers. They are traffic controllers or gatekeepers, if you like. They route between different subnets or different network segments. Routers have higher intelligence than the common layer 2 switch. They read destination addresses in data packets. They direct packets across multiple networks using predefined routes. They allow networks to scale efficiently, and they improve reliability with redundancy options. The top-level router on a network is typically the gateway. It links your local network to the outside world, the internet. Your gateway routes traffic between your network and external ones, manages DNS requests and responses, and it's essential for devices needing internet connectivity. And of course, a common device that is not used today at all is the bridge. Now that you understand the foundational network devices, let's chat a little bit about security. Network security is more critical than ever. We all read the security breaches making daily headlines. And for AV systems, since they rely heavily on IT networks, network security is essential. In its essence, network security prevents unauthorized access, protects sensitive data and infrastructure, and maintains integrity and reliability. To understand key security points, we need to recognize network boundaries, all ports, switches, routers, understand points of potential attack, and effectively collaborate with IT departments to ensure secure AV integration. Let's introduce some essential security concepts. Network access solutions is the first one we're going to talk about. Those control which devices can connect to a network and how they interact with it. Devices must comply with security policies before gaining network access. This ensures compliance with security standards and restricts device capabilities based on identity and the security posture of the organization. Another concept you need to familiarize yourself with is an access control list. Network devices use access control lists to filter network traffic. Access control lists define rules based on IP addresses, port types, source or destination address. They are crucial for AV setups requiring specific permissions. They enhance network security by permitting only the necessary communications. Another common one is the .1x. .1x is similar to a security checkpoint at an airport. Before devices access network resources, they must say who they are or authenticate their identity through an authentication server. This enhances security by preventing unauthorized access. They are commonly used in enterprise networks and they affect AV devices without robust computing capabilities. A common one you will find in the enterprise world is a firewall. Firewalls effectively inspect all incoming and outgoing traffic to ensure only authorized data passes through. Some firewall techniques are packet filtering. Those are done on preset rules that examine protocol headers. Some new generation firewalls can read up to layer 7. They often provide network address translation, concealing internal addresses by routing them through a public IP, and it also blocks unauthorized inbound connections. Firewalls also use port forwarding. It allows specific external traffic to reach internal devices securely. It's essential for AV equipment requiring remote access or monitoring. As an AV professional, you must clearly specify that requirements, that is, ports and protocols required for your equipment to function. Firewall rules must allow necessary traffic only without compromising network security. Precise configurations on firewalls ensures reliable AV system operation. So remember that you're going to collaborate closely with IT departments for optimal firewall management. So to quickly recap, DNS maps names to IPs, simplifies connectivity, switches switch frames between devices, routers direct data packets between networks, and gateways often connect networks externally, and network security protects networks through network access control lists, .1x, and firewalls. By understanding these concepts, you'll effectively bridge the gap between AV and IT, ensuring secure, reliable, and seamless AV integration. Thank you for watching, and I'll see you on the next one.